Hello, pre-calc students. It's time to talk about trig identities. Over the last few days, I've had you watching some videos of other mathematicians um, showing you some geometric proofs of these identities, and today I'm going to give you my take on it. So let's begin back at the beginning with this idea that we're trying to figure out what is the sine of alpha plus beta. Okay, alpha and beta being two angles. They can be in degrees or radians. And the idea here is, let's say if you've got alpha, okay, so alpha can be, okay, we'll make it this little guy right here. Okay, alpha, looking good. And if we want to know about the sine of alpha, well, that would be the height of that segment right there. So sine meaning the y value of that point. And again, this is on the unit circle, so we're calling this radius here 1. Now you also have beta, and it's some other angle. It could be smaller than alpha or larger than alpha. Let's just go with something like this. Oh yeah, pretend those are beautiful unit circles. Okay, I'm just doing quadrant 1. And we'll call this one beta. Now the idea here is if you took alpha and beta, and instead of putting them on two separate unit circles, what if you went on your unit circle here? Oh my goodness, it's so bad. It's just like in class. Okay, so here's alpha. And then instead of starting over back here at the x-axis, you begin where alpha left off, and you also put beta on there. So you end up at this new spot, and we're talking about it as alpha plus beta. What is the sine of this angle? Well, you might think, okay, well, I just want to go over here and I'll see what the sine of alpha is. Okay, so that'll be that. And then I'll see what the sine of beta is. And then I'll just add them together. But maybe you're starting to see that there's a problem there because we're not just stacking these on top of each other, they're rotating while you add them together as well. And if you want to see this in a more concrete way, let's actually put some numbers in there. So if I said, like, let's let alpha be 20 degrees. Okay, the sine of 20 degrees is about 0.34. Okay, let's let beta be 30 degrees. Oh, hey, special right triangle. The sine of 30 degrees is 0.5. Now, if this were as simple as adding them together, well, let's see, 0.5 plus 0.34 would give you 0.84 together. Okay, let's see if that's true. Well, alpha plus beta would be the same as 20 degrees plus 30 degrees. That's 50 degrees. So let's see, the sine of 50 degrees. Okay, type that in my calculator. Ooh, I get 0.766, which is not equal to 84. So that tells me that I can't just find the sine of each individual angle and then add it together to get the sine of alpha plus beta. There's got to be more to it. And there is. And it's not a secret. So this is the paper that I had passed out to you yesterday. And I'm really going to follow fairly closely to what the other mathematicians did when they proved this trig identity or trig formula. But I'll try to fill in some of the gaps, I think, of where the videos were the most difficult for me. I don't want you to think that I watched those videos the other day and I read this and it was so easy for me. I mean, I've been doing this work. I've done 3 pages of work on this, practicing and making sure that I understood it before I felt confident to share it with you. So if you listened to those videos last week and you thought, whoa, that just went over my head, that's okay. Yeah, it is a tough concept to follow these multi-step proofs, especially when you're still fairly new at using trigonometry. So let's see if we can break this trig identity down. The idea here is that we can't just do the sine of A plus the sine of B. Instead, the formula looks like this. But it didn't just fall out of the sky like that. It's not magic. What's missing are the steps that take this statement and turn it into this one. And that's what it means to write a proof, is you fill in the middle steps that make it easy to understand why the sine of alpha plus beta comes out to equal this formula right here. Okay, well, let's see if we can make it fairly clear. The first thing I like to do is see if I can figure out what I'm actually heading towards. I see that the sine of alpha plus beta, we've kind of got the same picture going on here that I drew a minute ago. It's just much neater. So let's let this be alpha, and this one over here will be beta. And I see that I've got multiple triangles hiding in here. Let's start though by looking at where I want to end up. Alpha plus beta causes this radius to go around the unit circle. So here it is. There's our radius. OM is 1 unit long. And when it ends up here at M, this distance right here, MQ, is going to represent the sine of alpha plus beta. So that's where I'm headed. The sine of alpha plus beta is equal to the length of MQ. Now, if I can figure out a formula for MQ, then we're getting closer to where we're going. MQ, I can see, has been broken down into a couple pieces down here. And I could write it as the sum of a couple smaller segments. I mean, there are 3 segments down here I could break it into if I wanted to. I think what I'll do is I'll break it into 2 segments, MR and RQ. Now, how do I know that that's what I should break it into? Mostly because I've tried this proof before, and when I tried to break it up into the other pieces, it didn't work. So what you're seeing right here is me doing this proof probably for the 5th or 6th time, because I hit a lot of dead ends. So I just want you to know, if you feel like you're not getting anywhere, that's how it goes. Like, that's how the process of writing proofs goes. You just feel like it's so easy for me because you only see my final version. But everybody, when they're writing proofs, when they're creating proofs, hits a lot of roadblocks and has to turn around and go back again. So, in my experience, I've found that if I can rewrite MQ as MR plus RQ, that'll help me get somewhere. Nope. And see, now I'm even messing it up again. I almost went down the wrong path. What I really want to break it up into is MT and TQ. So just like that, just that easily, I almost made the same mistake I've made before. But I'm going to rewrite MQ as MT plus TQ. And if you were writing a formal geometry proof right now, you'd have to say, oh, because the segment addition postulate. But I don't really need to go that in depth into your geometry theorems and postulates right now. Okay, so MT and TQ, here we go. Let's start doing some stuff with triangles and see if we can find some ways to write MT and TQ. First I'm going to look at is this triangle up here. That's the one where beta is the angle that's in the corner of it. And I'm just highlighting it in blue a little bit so you can focus your eyes on it. Notice that it's got 1 as its hypotenuse right there. What we're almost doing right now is ignoring alpha and pretending like the x-axis is right here along the bottom. So if you tilt your paper a little bit and ignore that alpha even exists, you could say, okay, well, angle beta goes up here. There's the hypotenuse, and then I can represent the x value and the y value of that triangle. The x value is going to be related to the cosine, because cosine is adjacent over hypotenuse. And the y value is going to be related to sine, because sine is opposite over hypotenuse. So let's write some formulas for these 2 sides of triangle OMN. Okay, so the first thing I'm going to write is that the cosine of angle beta is equal to the adjacent over the hypotenuse. Okay, the adjacent side compared to angle beta is this one right here. So that's side ON. And the hypotenuse is 1. Okay, now ON divided by 1 is just ON, so I can simplify this to say that, whoops, the cosine of beta is equal to ON. Okay, hang on to that. It's not an answer all on its own, but it's a good ingredient that we're going to need later. Let's also do that same thing with the sine. The sine of beta is equal to the opposite over the hypotenuse. And compared to angle beta, the opposite side is mn, and the hypotenuse is 1. Oops, crooked. Yep, there we go. Okay, so again, just like last time, dividing by 1 doesn't do anything. So I can really say that the sine of beta is equal to the segment mn. Okay, that tells me some good information about angle beta. Now, let's go look at angle alpha. And I wanted to start with angle beta because it's actually easier, even though alpha was our quote-unquote starting angle. Okay, here's this red triangle right here outlining ONP. Okay, when I have angle ONP right here, or triangle ONP, notice that this is not part of the unit circle. This hypotenuse right here doesn't make it all the way out to the edge of the unit circle. So this triangle doesn't follow exactly the rules of the sine is the sine is the y value and the cosine is the x value because it's technically not on the unit circle. However, we can adapt, and that's what we'll do. So let's look at alpha right here. And at the very least, I can say that the sine of angle alpha, can we see that? Yep, is equal to the opposite over the hypotenuse. Okay, well, compared to angle alpha, the opposite side is NP, and the hypotenuse in this case is ON. Okay, notice it's not 1. Again, the hypotenuse is not 1 because this triangle is not part of the unit circle. It's smaller. Now, good thing for us is that we just wrote up here that ON is equal to the cosine of beta. Now, you might also be thinking, okay, well, that's great, but where does that get me? Just follow my lead. We've got the sine of alpha, and then I'm not going to write opposite and hypotenuse this time. I'll write the part where I said NP, and now instead of writing ON, I'm going to substitute the cosine of beta, because just a minute ago we said that the cosine of beta is equal to ON. Okay, here I've got this statement, and I could solve for NP, and I could multiply both sides by the cosine of beta. Okay, what that's going to do is say that over here on this side, it's going to say the sine of alpha times the cosine of beta is equal to NP. Okay, there's another ingredient. Okay, so what do I know so far? I know ON, we just used that to write this statement. I know MN, that's this length right here. I know NP, this length right here. Remember that my goal, though, back up here at the top, is I want to write what is MT plus TQ. Okay, so MT plus TQ. Hey, I see something right now that is helpful. I just figured out a formula for NP, but look at how NP is related to TQ. They're both part of this rectangle, and since they're opposite sides, they should be the same length as each other. Now, again, if you were in geometry class, you might have to go through a few more steps to prove this perfectly, but we're just going to come in here and say that NP is equal to TQ because they're opposite sides of a rectangle. Okay, so hey, look back up here then. We're getting there. Remember that part of my formula that I want to prove is TQ. And we just figured out that TQ is the same thing as the sine of alpha times the cosine of beta. Okay, we're getting there. So now I need to know, okay, I've got this length right here and this length because they're the same. Now I just need to know how long this side is. Okay, this is, to me, the hardest part of this proof because we need to do a little angle jumping around. Pay attention to this red triangle right here. In this red triangle, if I shorten it up and only look at the little first part of this, this would be a similar angle to the whole entire one. That means that here is a 90-degree angle at the bottom. If this angle is alpha, that would mean that this angle right here is 90 minus alpha. It has to be the complement to alpha because they're both in the same triangle. 90 degrees is used up by this corner, and that means the other 90 degrees has to be split between these two angles. Okay, check out this angle right here and this angle right here. Those guys are what we call vertical angles. Remember that back from geometry class? That means that if they're vertical, we have a vertical angle theorem that says vertical angles are always equal to each other. Okay, so that tells me that this little corner right here is also 90 minus alpha. Now, this angle right over here is a 90-degree angle because initially when we set this up, remember that MN was the height or the Y value of this blue triangle. So that's a 90-degree angle. This angle right here is 90 minus alpha. So that we're talking about TRN right now, 90 minus alpha. And that means the only amount that's left over for this angle up here in this corner is alpha. Oops, wrong way. Alpha. That's saying that this triangle, MNR, is similar to angle ORQ. They're the same triangle. They have the same angles, but different sizes to their sides. So they are similar triangles. That helps us see that this angle right here is alpha, and that's the key to finishing this proof. Remember that I want to figure out what is this distance right here, MT. Okay, in our very last step, we're going to look at making it in black right now. Triangle MTN. Okay, this one right here. Okay, what is this length right here? Well, here's the right triangle, that black one. And I need to get a length for MT. Okay, this would say then, I'm going to write it over here, alpha, and I'm trying to figure out this side next to alpha. That's the adjacent side of alpha. Oops, I just wrote it backwards again, didn't I? Jeez Louise. Alpha. No wonder it looked so weird. Well, I guess I'm not a Greek alphabet person. Okay, so here we go. Where did I get lost at? Okay, we're going back to the cosine of alpha. We're using cosine because that uses the adjacent side. So adjacent over hypotenuse. And adjacent is MT. Hypotenuse is MN. Okay, I'm going to rewrite this down below. I'm going to say that the cosine of alpha equals MT. Hey, but what do you know? Just right above it, I have a statement that says MN can be substituted with sine of beta. So I'm going to rewrite this right here with sine of beta on the bottom instead of MN because MN is equal to the sine of beta. Okay, I'm going to multiply both sides by the sine of beta. Okay, that means I've got this statement that says the cosine of alpha times the sine of beta is equal to MT. Okay, there's our last ingredient. We are ready to put this recipe together. Why are we ready? Because go back to the very beginning up here. Remember what I was trying to prove? I'm trying to say that MT plus TQ is equal to the sine of alpha plus beta. We're trying to say this distance right here is our sine value. Okay, well, if I say that the sine of alpha plus beta is equal to mt plus tq, mt, I have a statement right here that says mt is the same thing as cosine alpha times sine of beta, and tq is, remember that tq is over here, tq and np are both equal to sine alpha cosine beta, and they have a plus between them. Okay, so NP and TQ were both equal to this statement. MT was equal to this statement. And that, my friends, is the formula that we have up above. Now, you'll notice that mine is in the opposite order from what's above. Mine says sine of alpha cosine beta in the second position, and cosine alpha sine of beta in the first position. But we know that when you're adding, it doesn't matter which term comes first. So that takes me right back up here to this statement. All of that work right there proves that the formula for the sine of alpha plus beta is really true. Like, we just proved that that formula really works. We showed where it comes from by using a whole bunch of triangles on that unit circle. Okay, is this a lot of work? Yes. Is it worth doing? Yes. If you're struggling with it, watch it again, try it again. My best recommendation is to try and see if you can repeat this without having my work right next to you. See how much of it you can remember just from your own memory, then come back and refresh and try to do it again. In the next video, I'll do one of the shorter ones. This is definitely, this one and the cosine are also very long proofs. But stick with it. It is worth the process. If your brain hurts, that means you're learning something new. Good job, everybody. I will talk to you soon.